Hello, this is Dr. Christy Patton-Lokes, a chemical engineering professor at Missouri S&T. These series of videos are going to be for the course Thermodynamics 1, Chemical Engineering 2110. We're going to be starting with Chapter 1, which is an introduction to the. Next, I'd like to talk about units and dimensions. First of all, if a problem is stated in American engineering units, the answer needs to be in American engineering units if you want to receive full credit. If it's in SI units, you want to give your answer in SI units. So the only reason to do anything else is if the instructions explicitly say otherwise. Now you may, in the process, work in any dimensions or unit system that you desire, but you want to make sure that your final answer is matching the style of the question, okay? Now, probably the hardest thing, if you remember from your physics and changing units, is using G sub C, which is just a conversion factor. Now, a conversion factor is something that is equal to 1, but it allows you to change units from something to something else. And we need G sub C because this is going to relate to our gravitational acceleration, and it's going to allow us to move from force units to mass units. In SI, this is simply 1 kilogram meter per Newton second squared is equal to 1, or a kilogram meter is a Newton second squared. In the American engineering units, it's a little more complex. It is 32.174 pound mass feet per pound force second squared. Or you could say 32.174 pounds mass is equal to 1 pound force times second squared per foot. Most of our problems are going to work with either pressure or temperature. In pressure, it's very important that we work with absolute pressure. Now, absolute pressure is going to be what I feel, or the gauge pressure, okay, and add that to the atmospheric pressure, what is in the surroundings around me. I'm going to make just one minor comment here. When you talk about the reading, engineers spell gauge pressure, G-A-G-E, and the instrument that you read that gauge pressure is spelled G-A-U-G-E. I know that's weird and confusing. Engineering goes back a long way before spelling was maybe so standardized as it is today. Now, if you'll recall, pressure is, now we usually think of it as force per unit area, but it's looking at that at an infinitesimal space. So if I shrink my area to a size of 0, it's the net change in force over that area, or again, we usually just think of it as force per unit area. Okay? At ambient conditions, for the sake of this course, we're going to assume that atmospheric pressure is 1 atmosphere, which is the same as 101.3 kilopascals, or 1.013 bar, or 14.696 psia. If you're at an actual location or you're doing an experiment, you would want to get the actual barometric pressure to know what P atmospheric is equal to. Temperature is our other very critical property that we're going to be dealing with constantly. And temperature is not easy to define. In fact, it's basically defined by what is known as the 0th law of thermodynamics. Now, I always argue that your mom knows the 0th law of thermodynamics. Okay, now what the 0th law says is if two bodies have equality of temperature with a third body, then they have equality of temperature with each other. Okay, now why I say your mom knows this one? Did you ever say, oh, Mom, I'm not feeling very well. I've got a fever. I'm going to stay home from school today. And what does she do? She takes your hand Usually she touches it to her own forehead, and then she touches it to your forehead. Okay? What she's doing is getting her hand and her forehead to a quality of temperature, and then touching you to find out whether or not that third object also has that equality of temperature. Now, we measure temperature, typically using Fahrenheit in this country and Celsius in the rest of the world. Okay? And we can do conversions back and forth between those, right? You probably remember the formulas. Right, if I knew the temperature in degrees C, I would multiply by 1.8 and add 32 to get temperature in Fahrenheit. Okay? Absolute temperature has no negative. Okay, and we'll get back to this again later in the course, but most of our calculations need to be done with absolute temperature. All right? Right, we can go to negative degrees C or negative degrees Fahrenheit. Those are very bitter cold days. But for the math, those negatives are going to really cause some unnatural problems. So we want an absolute temperature scale. So absolute temperature scales in English units or American engineering is the Rankine scale, and in SI units is the Kelvin scale. To convert those, so if I had temperature in degrees C, I'll add 273.15 to get temperature in Kelvin for SI. And in those American engineering, I'm going to take a temperature in degrees F and add 459.67 to get a temperature in degrees R. Now notice there's not a degree symbol with Kelvin. That is just math grammar for this. Occasionally, I'm going to want to do conversions between degrees Rankine and Kelvin, and that's not a problem. Take temperature in Kelvin and multiply by 1.8 to get temperature in degrees R. Now, one final thing is about delta T. Delta T is a change in temperature. So if I subtract two temperatures and I had, say, degrees C, and I had, let's go with 100 degrees C and 0 degrees C. The difference between those would be 100 degrees C, right? 100 minus 0. If I add 273 to each of those, I get 373 and 273, and I subtract and I get 100. The reason for that is that delta T is the same in relative or absolute. So, for instance, if I had 100 degrees C, if delta T was 100 degrees C, that is the same as saying that it is 100 Kelvin. And if delta T was 50 degrees F, that is the same as saying it is 50 degrees R. This concludes this lesson on Chapter 1, but there's more material still. So review this, make sure that you're solid on this, and then go on to the next lesson. Thank you very much.